Greetings! We're going to start second order systems now. So we've taken a look at first order systems, and from the work we've done, you should be able to handle basically any input now that would fit the method of undetermined coefficients, and you can handle an impulse. So now we're going to do this for second order systems, which is basically just the same thing, just a little more algebra. All right. So for our first system, I'm going to have, we're going to, excuse me, so here we have our second order differential equation, and now we have two initial conditions, y0 equals 2 and y dot of 0. So it's got an initial velocity equal to 4, its position is at 2. Now note that in general, any one of these could be 0, so you could be at a position of 2 when the thing's not moving. Or it could be moving, but it's actually at 0, whatever. All right, so conceptually, we do the same thing. We get the characteristic equation here, and then we factor it, and we look at this, we have two eigenvalues, -2 and -3. All right, now when we solve our problems, we need to do the transitory part of the solution is always done with the complementary part, okay, or the part that attenuates. And so we'll notice this is -2 and -3, so they're both stable. They're going to die out. All right. So here we have the complementary. So it's negative real roots. So the complementary, well, now we have two roots. We have two of these things. C1 e to the -2t, C2, so this will be a second constant, e to the -3. And so when you would put in initial conditions, we'll solve for the C1 and the C2. All right. So let's see here. We have, so this has just initial conditions. There's no input, so we're just going to get an initial condition response. All right, y0 equals 2. So if I look at both of these, if I set t to 0, I get a 1 and a 1. So I get C1 plus C2. All right. And then if I take the derivative of these things, I have a -2C1. When I put 0 into here, I get a 1. And a -3C2. And that becomes a 1. So that's what I have here. So now I have two equations, two unknowns, and you can solve for that. And I'll leave you to finish the math. You just take this, put it in this form. Actually, since this is, let's see, what did we have here? Oh, if I multiply this one by 2, I'd have 4 and a 2C1 plus 2C2. That's what I have here. And then this and that would just add them together. So you have -3 and a 2, so minus C2 equals 8, adding vertically there. So C2 is -8, stick it back in, you get C1 is 10. So here is our initial condition response. And if you look at this one, the root's at -2, so that's time constant of a half. This is at -3, that's a time constant of 1/3. Notice, this is longer than that, okay? So recall what we had. When we had a plot earlier, we had looked at roots. Remember, we had one at -5, and we said if you go this way, TS goes up, and if you cross this line, it becomes infinite. And as you go this way, TS comes down. So we have a -3 and a -2. This one is closer. This one will take longer. If we get the settling time, it's just 4 time constants. So the settling time here is 2 seconds, and this one is 4/3. So this dies off long before this one does. So we actually give this a term. When you have higher level systems that have multiple roots, this has 2. The one that dies out last is called the system or dominant time constant. You don't care. So think about this. If you want to control this system, this thing's done in 4/3 of a second. You don't do anything with this one until you fix this one. If this is too long to settle out, you change that to make this the longest one. Then you deal with that. So just giving you some insight for control. Everything, it's the thing that dies out last that you have to control. All right? That's this thing. All right? So here we have that logic we just had. E to the -2t goes to 0 more slowly. So the system has a settling time of 2 seconds. These roots have their own time constant, but the overall system settling time. Time constant, settling time, same concept, basically. The settling time for the system is 2 seconds, the thing that lasts the longest. So e to the minus 2t is said to be the dominant response because it dies out last. So this takes us to our next example here. So get a nice clean piece of paper up the top. So here I have y double dot plus 6y dot plus 9y. So, and I have initial conditions, same ones. And I'm still not putting in an input. Okay, and why? Because I want to deal with the complementary in here. It's got a hook to it. So notice if you factor this out, you would get lambda plus 3 quantity squared is the characteristic polynomial. So when you have roots that are repeated, okay, you don't just have c1 e to the minus 3t and a c2 e to the minus 3t repeated, because then you can just add them together. What you have to do is you do have one of them, and then you add a t to the next one. Okay? And let's suppose you had a third order system and we had lambda plus 3 to the third. Well, then you'd have a c3 t squared e to the minus 3t. So we just keep adding terms as you go. So we have one set of repeated roots, so we have an e to the minus 3t, and then you add a t in on the second one. All right? So that's why I wanted to do a little bit more. Okay, so we know how to handle that now. And so now we do the same thing. We take this thing, set t equals 0, and see what we get. So y0 equals 2. So if you let t be 0, notice this t out here wipes everything out. So we actually, this is kind of easy. We get c1 equals 2 directly. We can just stick t equals 0 here. We get a c1 plus 0. So 2 equals c1. Well, now we have to take the derivative of everything and set. So here I'm taking the derivative. It equals 4. So we have a minus 3c1, and then you let t be 0, so that's what's left. And then we have, these are the two terms for the rest. Okay, so we see I said let t be 0 for those. And here, I'll leave this you to do the work. Minus 6 plus c2 is what pops out, equals 4. Bring the 6 to the other side, you get c2 equals 10. All right. So now here we are. The initial condition response is 2 e to the minus 3t plus 10t e to the minus 3t. And here I comment, here's what we would do for a third order system. Now, yes, there is a t here, but if you were to look at this response, you would not know that it's there. So for each of these problems, you basically find your system settling time from your initial condition. It would die out. The slight change that happens in here because of that t would be very hard to pick up. All right, we will stop here.